Costanzo Bellini from the Department of Civil and Mechanical Engineering of the University of Cassino in Southern Lazio, in Italy, and I'm presenting a work entitled Short Beam in Plane Flexural Behavior of a Hybrid Titanium Lattice FRP Structure. This presentation is the outcome of a collaboration between our research team and another team from CIRA, the Italian Center for Aerospace Research. The aim of the present work consists in evaluating the effect of the skin material on the in-plane bending properties of hybrid structures, presenting additively manufactured metal cores and composite material skins. This work is organized in several steps. First of all, there is the definition of the case study. In particular, the cell was identified in terms of type and dimensions, together with the geometry of the specimens to be tested and the material to be considered for this work, that were titanium and different types of fiber composites. Then, the specimens were produced according to a two-step process. In the first one, the cores were manufactured through the Hebbian process. Then, the skins were added by procuring the prepreg layers on the cores. After, the produced specimens were tested, and the obtained results were presented and discussed. The characteristics of the lattice core are very important since they influence the mechanical peculiarities of the whole structure. As concerns the cell type, the octet truss lattice was chosen. This cell is a centric phase cubic cell formed by 24 beams, with an octaedron inside, formed by 12 beams. The cell side was chosen equal to 6 mm, while the beam diameter to 1 mm. The lattice core had a section of 10 mm for 9 mm and a length of 30 mm, while the skin thickness was equal to 1 mm for both types of material considered. This similarity was important for performing a meaningful comparison between the different types of specimens. The titanium powder adopted in the present research activity was made of the titanium-6 aluminum for vanadium alloy. As concerns the skins, two different types of fibers were taken into consideration, carbon and aramid. All the prepreg had the same epoxy resin as matrix. As concerns the manufacturing process of the cores, after having defined all the geometrical parameters, the first step consisted in the creation of a virtual geometrical model. For this purpose, the materialized magic software was adopted, that was able to draw a lattice structure in a specific volume. Once the CAD model was ready, it was exported to the slicing software of the 3D printer. The machine used was the Arkham A2X, while the relevant slicing software was the build assembler. Then, the machine was prepared for manufacturing run. The powder reservoirs were filled, and the process parameters were set. After, the vacuum was drawn in the manufacturing chamber. The electron beam was calibrated, and the manufacturing chamber was preheated. As the imposed temperature was reached, the specimens were built according to the typical sequence of a powder bed additive manufacturing process. At the end of the process, the chamber was cooled down and the specimens were extracted from the unmetalled powder and cleaned in a suitable chamber, using pressurized air and a sandblasting machine, while the final depowdering operation was carried out in an ultrasound bath. The prepreg vacuum bag process was chosen to create the composite skins. FRP prepreg plies were prepared and layered on the mold, together with the lattice core. All the layered specimens were covered with the release film and the breather fabric. Then the mold was closed with the vacuum bag. After the vacuum was drawn, the mold was positioned in the autoclave for curing process. The produced specimens were tested according to the 3-point bending scheme. The specimens were placed on two supports and they was loaded in the center by loading nose. This test is commonly used for sandwich structures, but usually the out-of-plane properties are determined. As aforesaid, in this work the in-plane characteristics are studied. Therefore, the load was applied perpendicularly to the skin direction, as visible in the figure. The span length was chosen equal to 20 mm, while the loading speed to 2 mm per minute. The data obtained from the experimental test campaign are reported in this graph, in terms of load versus displacement. In particular, a single curve was plotted for each type of specimen, that was representative of the results relevant for the 5 specimens tested for each type. For both CFRP and AFRP, maximum load of about 4000 Newton was recorded, even if that one of the latter was slightly higher. The maximum displacement at break was the same for both types of specimens, and it was equal to 1.8 mm. As concerns the shape of the curves, a sudden load drop after the attainment of the maximum load can be observed. The increasing load section of the curves was characterized by an initial linear part, even if a slight deviation from the linearity can be noted, followed by a first minor load drop, probably due to the breakage of some fibers. The subsequent part showed a nonlinear load increase with other load drops. Also in this case, this trend is caused by the breakage of more other fibers. Some images of the fractured zone were taken to inspect the fracture mode. As concerns the carbon specimens, the fiber failure was observed only in the lower part of the specimen itself, while fiber wrinkling was noted in the upper zone, just below the loading nose. The most interesting thing to highlight is that a sharp fiber fracture was observed in the lower part. As concerns the aramid specimen, also in this case the fiber tensile failure was observed, as for the carbon one, in the lower zone, together with the fiber wrinkling in the upper zone. The fracture surface of the carbon laminate was sharp and clean, while for the aramid a kind of fraying of the fibers was observed. A study about the in-plane flexural behavior of different FRP titanium structures is presented in this work. In particular, 2 different types of FRP skins were considered, carbon and aramid fibers, while the core, presenting a lattice structure, was made of titanium alloy. The lattice cores were made through ABM, while the skins were added through autoclave vacuum bagging. The experimental tests evidenced very similar mechanical properties for CFRP and AFRP structures, with a similar load displacement trend, even if the aramid one demonstrated a higher residual load capacity. However, different damage mechanisms were observed for the tensile filed fibers. The carbon fiber specimen presented a sharp fiber fracture, while for the aramid one, fraying was observed. Thank you for your attention.